All right, class. So this is sort of the big picture problem for our IR and NMR spectroscopy sections. And this problem is asking us to sort of come up with a plausible structure for a given molecule. The information that's given to us is the formula. So we've got C11H14O2. And we've got an IR spectrum with some peaks that are labeled and an NMR spectrum with all of the relevant NMR data for us. So I'm going to talk through sort of the strategy behind a problem like this, how I'd like you guys to sort of write everything out, and then how we can sort of come to a plausible structure for a final product, and then check to make sure that everything sort of makes sense. That we're proposing something that is consistent with the data. That's the goal here. Okay, so let's get started. So the first thing that I would do is look at my IR spectrum and sort of label what I see. Here we've got some peaks just below 3,000. So right away I'm going to say sp3ch. So we've got some alkane type sp3ch bonds that are stretching there. This 3033, that's going to be an sp2ch, so just above 3,000. That's my sp2 hybridized CH bonds. At 1759, so I think that this is pretty clearly a C double bond O. And then we can sort of think about, well, what type of C double bond O, what type of carbonyl stretch is that? So if we go to our table here is our C double bond O. We've got ketones, acids, about 1710. So again, we're at 1760 pretty much. We also know that conjugation is going to lower the frequency, so probably not a ketone or acid. Aldehyde 1725. Again, we're sort of, this is a little bit higher than those numbers. Esters, that's the highest one we have here, so about 1735. So I might be thinking ester here, looking at what else, fits. That's really the only thing I'm sort of finding on here. So that's going to be my guess at this point in time. So for this C double bond O, I'm going to guess, something like this with some other stuff going on here. So I've got a generic ester here. I'm going to put an R group here, and I'm going to say not a ring. And I'm going to say that that's not a ring on this other side of this, carbonyl stretch because this is so high. If it was conjugated, then that stretch would be lowered. It would be, I would expect it to be below 1735. But since it's above, I'm going to say definitely we don't have conjugation going on here. So I'm going to put not a ring for my ester. But I think that's a good start. 1600, that is going to be a benzene ring, right? So whenever we see 1600, we're going to think that that's a phenyl ring. So maybe that phenyl ring's over here, right? So we could say, well, maybe we've got some ring over here because there's clearly a ring in my structure. But I know that it's not on this side because this 1760 would be much lower. Conjugation would lower that frequency to below 1735 for sure. So that's the conclusions that I can draw from my IR. And these labels, I think, are very important, right? We need to have this sort of information. The sp2ch, that can come from my ring, so that makes sense. This other R group, this sort of suggests that that's going to be some sort of alkane, ethyl group, a propyl group, something like that, probably coming off as this R group because I have these sp3chs. So then let's go to the NMR and see what we can find in the NMR. This is how I'm going to present the NMR to you, and it's sort of hard to see, it's sort of hard to interpret this. So what I would really recommend is labeling all these peaks. So out here, I've got a 2-high doublet. This one is again a 2-high doublet. So writing the information on, the actual NMR spectrum makes it easier to interpret. So here at 2.5, this is a 2-high triplet. This peak here at 2.3 is a 3-high singlet. So that singlet, that's, right away I'm sort of saying, oh, that's pretty interesting. There's a methyl group there, 3-high, it's probably a methyl group, and it's isolated. 3-high singlet means, a methyl group that's isolated from other things. It's not part of an alkane chain. Down here at 1.8, I've got a 2-high multiplet. So M means multiplet, so multiple things going on, more complex splitting. And then at 1.8, or excuse me, at 1.0, I've got a 3-high triplet. So a 3-high triplet, to me, a 3-high triplet indicates I've got something like this. So this methyl group here, that would show up as a 3-high triplet because it's bonded to this methylene linker. So that would, split this methyl group into a 3-high triplet. This is coming right at about 1, so that makes sense for a methyl group. If we turn this table over and we look at where a methyl group is going to come on an alkane, 0.9. So right away, this to me says I've got some sort of ethyl group. For this CH2, I think I've got sort of, if this say was linked to my carbonyl carbon, then I would expect to see some sort of 2-high quadruplet, right? 2-high quadruplet. I don't see that, but this CH2 is probably linked to something else, and then it's this multiplet here, right? Because I've got to have, a 2-high something. It's not going to be this 2-high triplet because this would be a quadruplet at least. So this methylene is probably this peak here. And then that's probably linked to something else. So there's going to be some other, CH2 or something else here that I'll have to deal with. So far, that's pretty good. The next thing I might say is, well, let's deal with these 2 peaks out here. These I think are very indicative of something. So to me, I'm going to say that these peaks out here, those are probably going to be something on a ring. So if I look at where my phenyl, my aromatic, phenyl H shifts come, approximately 7.2. We're right here at 6.9, 7.1. So pretty clearly, I think we've got a situation like this. I've drawn here where I've got a symmetric phenyl ring, right? So it's symmetric, a mirror plane right along here. So 2 of these, right? A 2-high doublet and a 2-high doublet. That's what I would expect for something like this. Now, this sort of, reminds me of this 3-high singlet, and that 3-high singlet could be a benzylic, a phenyl methyl, so phenyl with a methyl group on it, and that comes at approximately 2.3. So my 3-high singlet, well, that's exactly at 2.3. So I'm going to put a methyl group here. I really think that matches up really nicely, where I would have an R group coming off here. 3-high singlet would be my methyl group on that benzene ring. That matches up really nicely. These I think are clearly 2-high doublets, on that ring, because I've got that mirror plane here. So, this, I think something like this is definitely part of my structure. So let's sort of bring it together a little bit here. We know that we have an ester. We know that we've probably got a ring over here. Now we're going to add that methyl group right over here. That takes care of this peak, and this peak. I think we earlier said we've got a 3-high triplet from this methyl group. This multiplet is probably this methylene. So that leaves this peak over here, a 2-high triplet. So right away I'm going to say, well, that could be a CH2, CH2, CH3, a propyl group, because this methylene would be split by this methylene to give a 2-high triplet. This would be a multiplet because I've got, splitting from both of these groups. And then this would be a triplet as well, so 3-high triplet. So something like this, a propyl group, would also make sense. So I think I'm getting pretty close here. I'm going to go ahead and draw out what I think. So I think this structure here, where I've got a propyl group bonded to my carbonyl carbon, so I do not have conjugation here. Then I've got this ester, and then I've got my ring off of the other end of the ester. I think this is consistent with all of the information that I have here. So then the next exercise would then be to go back through, so label all of these, H, 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 and then just double check to make sure that everything is consistent with all of the data that was presented. Do the assignments, so assign where you think each proton sort of belongs in all of the proton NMR spectra. But I think this is probably a very plausible, good structure to come up with. The other thing now that I forgot, we were given the chemical formula, so don't forget about that. C11H14O2. So let's go ahead and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So C11. H14, so here's 7, 8, 9, 10, 11, 12, 13, 14, and then 2 oxygens. I think we're in good shape. This looks pretty good.